Okay, let's jump right into this deep dive. It's kind of mind-blowing when you think about it. Since what, 1995, the first confirmed exoplanet,
Yeah, around then.
and now we're talking over 4,000 known planets outside our solar system. Just staggering.
It really is. The pace of discovery has been incredible.
And the ways we find them are pretty clever too, right? You've got this star wobble, uh, radial velocity,
Radial velocity, exactly. Seeing the star move back and forth from the planet's gravitational tug.
and then there's gravitational lensing where light bends.
Right. Bending around massive objects, revealing things behind them. Less common for finding planets, but it works.
Orbital timing variations too, I think.
Mm-hmm. Tiny changes in the timing of things we can see, hinting at something we can't.
But the big one, the one that's found the most, that's the transit method, yeah. Watching for that tiny dip in starlight.
Absolutely. That's been the most prolific method by far.
Yeah.
It's like watching for a tiny, tiny eclipse when a planet passes in front of its star.
And NASA's Kepler satellite was the champion of that, wasn't it?
Oh, definitely. Kepler was a game changer. Launched in 2009, ran till about 2018.
It just stared at one small patch of sky, didn't it? Like, relentlessly.
Yeah, a fixed gaze. About the size of your hand held out at arm's length, that
Yeah.
patch of sky. But by staring for so long, it found over 3,000 transiting planet candidates.
Incredible numbers. And within that haul, a lot of focus is on the terrestrial ones, the rocky planets.
Right. The ones that are, roughly Earth-sized,
Yeah.
maybe a bit smaller, maybe a few times bigger.
Like our inner solar system, Mercury, Venus, Earth, Mars, made of rock and metal.
Exactly. The thinking is they're mostly silicate rocks, metals.
Mhm.
Probably have a structure similar to Earth's, potentially.
So a metallic core, a rocky mantle,
Yeah.
that kind of thing.
That's the standard model, yes.
Mhm.
Unlike the gas giants, which are fundamentally different.
Right, Jupiter, Saturn. They likely grab their atmospheres straight from the disk the star formed from.
Whereas these rocky worlds, they probably developed secondary atmospheres.
Secondary, how does that work?
Well, through things like volcanic outgassing gases released from the planet's interior, or maybe from impacts, like comets or asteroids delivering water and other volatiles later on.
And the atmosphere is key for habitability, obviously.
Absolutely crucial. It dictates surface pressure, temperature, protection from radiation.
Now, Kepler did find some of these rocky types, right? I remember names like Kepler 20, Kepler 42.
It did, yes. Several systems with terrestrial-sized planets.
But there was a catch with many of those early ones.
Yeah, the catch was their orbits. Many of them were incredibly close to their stars, like really close, orbiting just a few Earth days.
So ridiculously hot, like Mercury, or even hotter.
Exactly. Way too hot for liquid water on the surface, which is, yeah, generally considered the key ingredient for life as we understand it.
Why did we find so many of those hot ones first? Just easier to spot.
Pretty much. Short period means more transits in a given time frame, so statistically you're more likely to catch them, especially in a survey like Kepler's initial run. It was, like you said, easier, the low-hanging fruit, in a way.
But the field hasn't stood still. We're finding others now.
Oh, definitely. The progress has been immense. We're now finding terrestrial planets further out from their stars.
In the habitable zone.
Exactly. The zone where conditions might be right for liquid water, and finding rocky planets there suggests they could actually be, well, really numerous.
Okay, let's unpack that habitable zone idea. It sounds simple, not too hot, not too cold, but it's more complex.
It is. The basic idea isn't new, actually. People were thinking about Earth being just right centuries ago. Richard Bentley, for instance.
Huh, really? That far back?
Yeah, the intuition was there. But the modern definition is more technical. It's the region around a star where a planet's surface temperature could allow liquid water to be stable.
So it depends on more than just distance.
Right. You need sufficient atmospheric pressure, too.
Mm.
Too little, and water just boils away or freezes. And the temperature needs to support the kind of organic chemistry we think life needs.
But are we being a bit Earth-centric here, assuming water is the key?
That's a fair question, and scientists debate it. But based on the only example of life we have as liquid water, seems fundamental. So it's the most practical criterion to start with for our searches.
Makes sense. So where are we now? How many potentially habitable ones have we found?
Well, as of early 2022, the Habitable Exoplanets catalog listed, I think, over 20 candidates.
Any famous ones?
Sure. Kepler 1649b is one, Proxima Centauri b orbiting our nearest neighbor star, and several in the TRAPPIST-1 system are really interesting.
TRAPPIST-1. That's the one with like 7 Earth-sized planets around a small, cool star.
That's the one. Fascinating system. But classifying these as potentially habitable is tricky.
How so? What makes it complex?
Because we have limited data. We estimate size, we calculate the stellar flux, the light hitting the planet, but we often don't know much about the actual atmosphere or the star's activity.
Like solar flares and things.
Exactly. A planet could be in the right temperature zone, but if its star is constantly blasting it with radiation, it might not be so habitable after all. So there are debates about the exact boundaries and criteria.
Okay. And pushing this search forward, we've got two big new players on the scene, right? TESS?
Right, TESS, the Transiting Exoplanet Survey Satellite, launched April 2018. Kind of Kepler's successor, but with a different strategy.
How different?
Instead of staring at one patch, TESS is scanning almost the entire sky, looking at brighter, closer stars over a huge area 400 times what Kepler surveyed.
Wow. So the goal was different.
Yeah, the initial 2-year mission aimed to survey about 200,000 nearby bright stars, hoping to find at least 50 Earth-sized planets around them.
What's the advantage of looking at closer, brighter stars?
They're much easier to follow up on, especially for studying atmospheres, which is the crucial next step. Kepler found amazing things, but many were faint and distant. TESS finds targets ripe for detailed study.
And the other big player, the James Webb Space Telescope, JWST.
Yes. JWST, launched December 2021, a truly revolutionary observatory. While it does many things, a key goal is analyzing exoplanet atmospheres.
Really digging into what they're made of?
Exactly. Looking for the chemical fingerprints of gases. Can it find water vapor, methane, oxygen, things that could hint at habitability, or even biosignatures?
Biosignatures, signs of life itself.
Potentially.
Yeah.
Certain combinations of gases like oxygen and methane together in large amounts are hard to explain without biology, at least based on our understanding. JWST is our best bet right now for spotting those.
So TESS finds the candidates nearby, and JWST zooms in for a closer look.
That's a good way to put it, yes. A powerful synergy.
And TESS has already found quite a bit.
It has. By early 2022, around 200 confirmed planets and maybe 5,000 candidates needing confirmation.
I remember its first discovery was pretty quick, Pymensi b.
Yeah, September 2018.
Yeah.
And its first Earth-sized one, HD 21749c, in April 2019. Though that one's also quite hot in 8-day orbit.
So, because TESS scans the sky more broadly, it doesn't stare at stars for as long as Kepler did. Does that affect finding Earth-like orbits, like year-long orbits?
It does. For a sun-like star, you need to watch for a long time to catch the 3 transits needed to confirm a planet with a 1-year period. TESS's initial survey often didn't observe individual stars long enough for that.
But it's good for other types of stars.
Yes, especially dimmer, cooler stars like M-dwarfs. They're very common. Their habitable zones are much closer in, so planets orbit faster. TESS is great at finding potentially habitable planets around M-dwarfs, even with shorter observation times.
And those planets could still get Earth-like amounts of light, even orbiting faster.
Exactly, because the star itself is less luminous, so the just right distance is much closer.
You mentioned earlier, though, it's not just about the light, the stellar flux. Other things matter for habitability.
Oh, absolutely. Stellar flux and atmosphere are maybe the biggest drivers of surface temperature, sure. But you also have to consider the star type. Is it stable, like our sun, or prone to flares?
Flares sound bad for life.
They can be. High UV radiation, frequent powerful flares. They could strip away an atmosphere or sterilize a surface.
What else? You mentioned metallicity.
Right, the star's composition, the amount of heavier elements. It affects how planets form in the first place. And then there are tidal effects.
Like the moon and Earth, but stronger.
Potentially much stronger, especially for planets orbiting close to small stars. It can lead to tidal locking, where one side always faces the star.
Ooh, like our moon. One side baked, the other frozen.
That's the concern.
Or
Makes it harder for life to get a foothold, perhaps. So, yeah, it's a complicated picture, much more than just being in the Goldilocks temperature zone.
Okay. And going back to the transit method, you said you need 3 dips in light?
Generally, yes, at least 3. 2 gives you a possible period, but the third confirms it's regular and repeating, helps rule out star spots or other stellar activity mimicking a planet.
Right, gotta be sure. Which leads to some cool work combining test data with other missions. You mentioned Gaia.
Yes, the Gaia mission is crucial here. It's mapping the positions and distances of billions of stars with incredible precision.
And knowing the distance accurately helps how?
If you know the exact distance, you can figure out the star's true brightness, its luminosity. Without that, you can't accurately judge the planet's size from the transit depth or calculate how much energy it receives, which is vital for defining that habitable zone correctly.
Got it. So Kaltenegger and her team used test data plus Gaia distances.
Exactly. They created the TESS Habitable Zone catalog. They looked at the first 2 years of TESS data, cross-referenced with Gaia's second data release, DR2.
What were they looking for?
They identified stars. TESS had watched long enough to potentially see 3 transits of a planet receiving Earth-like levels of radiation. Using Gaia's precise stellar data, luminosity, temperature, radius, let them define those habitable zones much better.
And what did they find? Lots of targets.
They flagged over 4,200 stars within about 700 light-years that could host such planets. Nearly 740 of those are within 100 light-years. Quite close.
Wow. And had Tess actually seen planets there yet?
At the time, only a few of those stars were known planet hosts. But crucially, TESS had observed over 600 of them long enough to potentially detect planets throughout their entire temperate habitable zones, even out to where Mars is in our system.
So it's like a prime hunting list for Tess's ongoing mission.
Precisely. These Gaia-characterized stars are top candidates for finding potentially habitable worlds nearby. It's very targeted now.
Which kind of flips the perspective, doesn't it? Instead of us just looking out, who might be looking back?
Exactly. If aliens had telescopes like ours, where would they need to be to see Earth transit the sun?
So there's an Earth transit zone out there.
Effectively, yes. A specific slice of the sky. If you're in that zone, you'd see Earth pass in front of the sun every year. It's defined by Earth's orbital plane, the ecliptic, projected outwards.
Has anyone estimated how many stars might be in that zone?
People have tried. Heller and Pujitz in 2016 suggested maybe up to 10,000 sun-like stars, G&K dwarfs, could be positioned within our transit zone.
10,000! That's a lot of potential viewpoints.
It is. From those systems, observers could, in principle, detect Earth and maybe even infer it's habitable.
Any other estimate?
Wells and colleagues in 2018 looked at how many of our solar system planets might be visible from elsewhere. They figured a maximum of 3 could be seen transiting from any one point.
Interesting.
And they estimated maybe only about 3 known temperate Earth-sized planets around similar stars happen to lie within our transit zone. So it's possible someone out there, if they're looking at those specific stars, could already know about us.
That's wild. And Tess is actually helping with this reverse search, too.
In a way, yes. Kaltenegger and Pepper in 2020 used TESS and Gaia data again. They found over 1,000 main sequence stars within about 300 light-years that are perfectly placed to see Earth transit the sun for at least 10 hours.
1,000 stars with a front row seat to Earth's transit, mostly M dwarfs, you said earlier.
Mostly M-types, then K-types, then G-types like our sun. And the cool part is, TESS, in its extended mission, is actually spending more time observing the ecliptic plane.
The exact region where these potential observers would be.
Exactly. So TESS could literally find a planet in a system that has already detected Earth. It's a fascinating possibility. Cosmic peekaboo, as you said.
Amazing. Now, shifting gears slightly but related. Finding habitable planets is one thing, but actively searching for signs of technology is another. That's where Breakthrough Listen comes in.
Right. Breakthrough Listen, a huge $100 million project started in 2015. Its whole goal is to search for evidence of technological civilizations, not just habitable conditions.
What are they looking for? Radio signals, lasers.
Both, primarily. They use big radio telescopes and optical telescopes to scan for signals that look artificial. Things like narrowband radio signals, which nature doesn't really produce, or maybe pulsed laser signals that stand out.
And they're teaming up with TESS people.
They are. Since late 2019, there's been a formal collaboration. Breakthrough Listen is adding TESS objects of interest, stars, TESS flagged as potentially having planets to their target list.
Using Gaia data to help choose the best ones.
Exactly. Gaia helps pinpoint the stars and understand their properties. And they're even timing some observations for when TESS planets are expected to transit. The idea being, maybe that's a logical time for a civilization to send a signal our way, if they know we're here or might be looking.
A clever strategy, combining the planet hunt with the SETI hunt.
It's a really smart synergy, using all the tools we have.
So, wrapping this up, it feels like we've moved into a whole new era of exoplanet science. We went from, do they exist, to finding thousands, and now we're really zooming in on the potentially habitable ones.
Absolutely. The focus has shifted dramatically. It's less about sheer numbers now and more about characterization, finding those rocky worlds in the right place.
And TESS and Gaia are just fundamental to this current phase. TESS finding the nearby transiting candidates across the sky.
And Gaia giving us the precise stellar data, especially distance, to really understand those stars and nail down their habitable zones. It's a powerhouse combination.
And still, that idea of flipping the perspective, that potentially hundreds or even thousands of nearby stars have the perfect angle to see Earth crossing the sun.
It's quite profound, isn't it?
It really is. It leaves you thinking. If those vantage points exist, what does that imply? Could someone already know we're here? And initiatives like Breakthrough Listen are actively looking for those hello signals.
It really underscores the scale of the universe and perhaps the increasing probability that we're not alone. Maybe the question isn't just, are we alone, but has someone already noticed us? Something for you to ponder.